Good afternoon and welcome again to the first plenary talk of the week. As I mentioned this morning, every day except Wednesday that we have the mid-Congress excursion, we will have a special plenary lecture. And in all cases, they will be introduced by our honorary chairperson, that is Judy McKenzie. So I will leave the floor to her that will introduce our first speaker today then.
Thank you, Danielle. I'm very pleased to introduce the first plenary speaker of the 19th International Sedimentological Congress, Dr. Carlota Escutia. Carlota, after completing her doctoral studies in 1992, she left Europe, traveled across the Atlantic, and ended up in California, where she did a 2-year postdoc at Stanford University. Afterwards, she had a 4-year stay at the U.S. Geological Survey. But I think her real career begins in 1998 when she had her first ocean drilling cruise, and that was ODP Leg 178, where they were drilling offshore the Antarctic Peninsula. And she sailed on this cruise as a stratigrapher and it's a sedimentologist and seismic stratigrapher. This experience just happens to coincide, or maybe it explains her next move from the shores of California, of the Pacific Ocean, inland to Texas, to College Station, University of Texas A&M at College Station, Texas, where she worked for the ocean drilling program as a research scientist and leg project manager. And here she participated in 2 further ocean drilling cruises. Returning to Spain in 2002, Carlota became part of her current institute in Granada, at the University of Granada, first as a prestigious Ramón y Cajal investigator, and subsequently as a working as a research scientist with the Spanish Research Council. Her return to Spain and the beautiful mountains of Andalusia did not extinguish her love for ocean-going interests and ocean drilling research. She continued to develop her long-term ocean drilling strategy as a lead proponent for a new drilling proposal to return to the Antarctic to study the Cenozoic East Antarctic ice sheet history. Her dream to drill in the Antarctic came true with the scheduling of IODP Expedition 318 in early 2010, and she set sail as the co-chief scientist to study the Wilkes-Land glacial history. And I don't have it with me, but there are some wonderful YouTube videos of the Penguin TV and the work that was done on that cruise. They're really beautiful, and I think if you want to learn more about what happens on board the JOIDES Resolution in the Antarctic, you must go and look up these YouTube videos. Carlota's research interest over the years is focused on seismic stratigraphy and sedimentological studies of clastic continental margins in both high and low latitudes, and is directed at elucidating aspects of the following overarching themes: global environmental and paleoclimatic change, geohazards, and resource assessment. She will surely touch upon a few of these topics in her, as expressed in the title of her plenary talk, Sedimentary Records of Ice Sheet Behavior During Past Warm Intervals and Ocean Drilling Strategy. Carlota, please. Please welcome Carlota Escutia.
Thank you. Yeah? Okay. So thank you very much, Judy, for this very nice and kind introduction, and I also like to thank you and the ISC organizers for inviting me to be here to talk to you about how we interpret sedimentary records to understand ice sheet behavior in polar areas, but of course I will concentrate my talk in the Antarctic. I have divided the talk in 3 parts. First, I'm going to try to make a case as convincing as possible of why we need sedimentary records from polar areas, and more specifically from Antarctica. And once I have done that, I will going to show you two case studies of why, of the state of knowledge of what we have in two time slices of the Cenozoic, the early Eocene greenhouse world, and this is before ice sheets existed in any of our poles, and then the early Pliocene warmth interval. Finally, I will end up the talk with the strategy that has been built by the community to try to get the records that we're still missing to get a full picture. And the idea is that we want to learn about past ice sheet behavior to really inform what the future changes may be under the climate change, warming that we have these days. So polar areas are an important component of the Earth's climate system. Here in this cartoon, you have many of the components of the climate system. Any change we do in any of these components affects the rest of the components. And of course, ice is an important component of the Earth's climate system. And the ice affects the albedo. This is these very white shields that are in the Arctic and the Antarctic are responsible for how much sun radiation gets reflected back into space. If these were not here, this heat would be absorbed by continents and oceans. They are the places, both Greenland and the Antarctic, where the bottom waters of our oceans form. These are the key components of the ocean thermohaline circulation, which of course is this conveyor belt that distributes heat in our planet. They are extremely relevant for sea level changes. As we grow and decay continental ice sheets, then we either rise or lower global sea levels. And of course, the existence of sea ice, it does have a great effect in how the exchanges between the air and the oceans take place, and also marine productivity. So this is just to give you a taste of the relevance of polar areas. But despite the relevance, the polar areas are not very much sampled. They're quite unsampled. And this is just to show you a picture of how we can measure this fact. This is the history of ocean drilling from 1968, starting with the deep sea drilling project, to 2013, the integrated ocean drilling program that just ended in September last year. And we see that during these years, there are 236 expeditions or legs, and only 17 have been conducted in latitudes that are north or south of 60 degrees latitude, and 7 of these are in the Antarctic. And the reason why there is so little is not one to overlook. These areas are remote, and these areas are very hard to access. And this is one of the operations that was conducted by the Integrated Ocean Drilling Program during Expedition 302 in the Arctic. This was operated by ECOR. This is the European Consortium for Ocean Drilling. Please visit the booth that is just situated outside this room in front. This is the IODP booth. There is ECOR representatives and IODP representatives there, and they can inform you about this great program and possibilities of how to participate. But this is a very complex operation in areas that are ice covered all year. And it required for 3 ships, 1 that was conducting the drilling and 2 that were just there to manage the ice. So you can imagine the complexity of these operations and also the cost. When we don't have permanently covered areas of ice covered areas, we do face icebergs in the shelves of Antarctica and also around the Arctic. And these icebergs have the bad habit of being attracted by the drilling pipes, and therefore we are continuously having to stop operations and trip pipe up and bring it down again, which prevents the drilling greatly. So those are very challenging. And of course, these are areas that have very bad weather conditions. In Antarctica, we do have katabatic winds that pick up in no time, and they go into hurricane wind speeds, creating these big storms under which we cannot operate. So This is why there is not so many operations in these polar areas. Here, in addition to the 7 expeditions that have taken place in the Antarctic by the DSDP, ODP, and IODP, here marked by the green dots and the green star, I have added marine sediment records that have been collected by other drilling programs, such as the ANDRIL. This is a program that drills through the ice shelves into the water and then to the sediments at the bottom. And these have been conducted mainly in the Ross Sea. ANDRIL is the latest of many programs that preceded ANDRIL that use mining technology for this drilling. And then there's the US National Shell Drill Program that is funded by the US National Science Foundation, which did some operations to two expeditions into the Antarctic Peninsula area. So overall, this is the distribution. You can see that, well, we do have some areas that have been sampled. Many areas are completely unsampled. And in the areas that have been sampled, we sometimes have either distal records, that means deep sea records, which is going to pick up the oceanic signal. And we do have few coastal records that are going to be the ones picking up the signal of grounding ice advancing and retreat across the continental shelves. Just to give you a perspective, here is Antarctica compared to Europe. If we had the amount of sampling that we have right now in Europe as we do have in Antarctica, you could see the difficulties of reconstructing paleoenvironments through Cenozoic in the different areas. Because right now we may be just having a very regional, local picture and not a continent-wide picture of what's happening in Antarctica. And as you will notice, I mainly talk about marine records. And that doesn't mean that they're the only records that we have around Antarctica. But when we consider that 99.7% of the Antarctica surface is covered by ice, you can see that the outcrop records, they're extremely valuable. When we have them, they're a wonderful snapshot into past ice sheet behavior and ice sheet history, but there are very few outcrops that we can draw from. Subglacial records, those, we love to have them. The technologies are now coming into play to be able to access them. Lake Vostok has now almost reached the lake sediments. Lake Ellsworth has had some technological failures. The WISR program from the US National Science Foundation has accessed some of this record, but the technologies are just now becoming into play. So yes, most of what we know right now comes from the marine records that have been collected by the ocean drilling programs and ANDRIL and Shelton. Here is a graphic of the Cenozoic climate history from 45 million years ago, here at the bottom left of your screen, to present. At the bottom we have the record of temperature that is drawn from this gray wiggly line that is the isotopic delta O18 record of Zakos et al. In 2001. And from 45 million years ago to 34 million years ago, this record is purely temperature because the ice sheets did not exist in Antarctica and they did not exist in the northern hemisphere. After that, the record is a mixture of ice volume and temperature, and this record needs to be detangled. What I want to draw your attention here is, well, that if we are looking at the last report of the IPCC, the Intergovernmental Panel for Climate Change, Report 5, the most pessimistic scenario has temperatures for the end of the century reaching 4 degrees centigrade. The most optimistic is about 1.8 degrees centigrade. If we take this most pessimistic scenario back in time and we look at the temperature line, it brings us back to temperatures that the Earth has not experienced in about 10 to 15 million years ago. And when we look at the other panel, the CO2 record, and we look at the projections for the IPCC in 2000 and at the end of the century, we do have, again, with the most pessimistic scenario, is taking us back to times before the ice sheets even formed in Antarctica. To note is that when we have these very high temperatures, it does correspond lightly with a higher CO2 record and higher sea levels, and as CO2 records are lower, we get cooler climate and sea level. And there is not a one-to-one correlation, it's just an overall thing for you to notice. The Antarctic ice sheet, as I mentioned, forms at 34 million years ago. This is a very sharp shift in this isotopic curve. This is instantaneous time, almost geologically. It took place between 300,000, 400,000 years, and these continental ice sheets formed in Antarctica. The permanent northern hemisphere ice sheets did develop 3 million years ago. So if we are to look into what happened to the ice sheets during times of elevated temperatures and CO2 in the past, so they can inform us of what it could happen in the future, Antarctica is a good place to start looking for. And this is what I wanted you to hopefully, I made the case for polar areas and Antarctica being a relevant spot, even if it's a nasty place, a beautiful place to go and do research. So the records that we have obtained until now are mainly collected by the ocean drilling programs from the deep sea drilling project starting in 1968 to the program that is now ongoing, the International Ocean Discovery Program. These are the programs that are key to collecting these records that we need, and they have been key to providing the knowledge that we have acquired. Again, I don't want to miss this UNDRILL program, which is the one that drills with a rig from the ice shelf into the sediments, which operates, of course, closer to coastal areas, but they have a very, very good record of recovering glacial sediments, which is not an easy task. And it's very difficult when you're operating from from a ship which is bouncing up and down. So what is motivating us is to answer questions such as this one. And these are not all, but they are good examples. Is how do ice sheets and sea level respond to a warming climate? How the Antarctic and the Southern Ocean were different under different high CO2 conditions. 400 ppm is what we have today. 600 ppm is what we will be coming at soon, and then the 1,000 ppm, which is what is projected to the end of the century. What are the forcing mechanisms? We still don't know what are driving these changes. We still don't know what are the thresholds, and our dating is usually not good enough, of high resolution enough, to really talk about rates. We're not there yet. Interestingly, we still don't know much about the opening and closing of the gateways around Antarctica. The Tasman Gateway, which separates Antarctica from Australia, has been better studied and known. There is more records for it. But the Drake Passage, for example, which separates the Antarctic Peninsula from South America, there is great controversy about when that opens, when it deepens, to allow this Antarctic circumpolar current to isolate Antarctica thermally. And how does the ice sheet variability does affect the formation of these Antarctic bottom waters that are so important for the thermohaline circulation? So I'm just going to go ahead now and give you 2 case studies to show you in the time available a little snapshot of what we know, where we're at, what we're missing. And for this, I have chosen 2 intervals that are starting to be better known, we could say. And this is the Eocene greenhouse world. These are right here, before 34 million years ago, before the ice sheets in Antarctica formed. And this is again a time where CO2 levels were very high. And here's the predictions of the IPCC. Is 936 ppm CO2 for the end of the century. But when we join all the greenhouse gases and turn it into CO2 equivalent, that puts us back to 1,313. And the other period that I want to have a look is the warm Pliocene period. This is a time that is similar to today with 400 ppm CO2, and the predictions of the IPCC is CO2 of 421 for the end of the century. When combined all the greenhouses into the CO2 equivalent, it puts us almost to 500. So let's look at the Eocene. Again, this is the time, high CO2, high sea levels, around 660 meters higher. Also, some between 60 and 80, depending in some of the literature. And again, there is a time where we have the Eocene, early Eocene climatic optimum, which is here. These are the highest temperatures that were recorded. And then we have cooling in the middle Eocene, and the end of the cooling ends up in this very sharp transition that we know as the Eocene-Oligocene transition. That's very, very fast in geologic time. And then at the OI1 event, this is when we already have a continental ice sheet in Antarctica, and we have gone from what we call the greenhouse to the icehouse world. So this is actually a new stack that has come, that is now impressed by Madelcy et al. And it's very nice because it does separate the stack from high latitudes from low latitudes, which is, it does help a little bit. So how was the early Eocene and the middle Eocene in Antarctica? This is one of these precious outcrops that I was mentioning. This is an outcrop. I will always have a map here to show you with a red dot where we are in Antarctica, since I will be showing different places in different locations. So this is the Antarctic Peninsula, and this is the rock record of the Seymour Islands. And here we have these 3D imprints of what is similar to what is the Araucaria auracana. These are conifer branches, and if we are to look at something, an environment that is similar to what these conifers lived in, we would have to go probably to the Chilean Andes, and that will indicate that these rocks indicate that the climates here were cool and they could withstand snow. If we now go to the Wilkesland margin, now we're here, opposite from Australia. This is the margin that is opposite from Australia. On the left, you have the lithostratic column of what was drilled. We drilled 1,000 meters, and we had a record at this site of late Miocene to early Eocene. The objective of this site was actually to understand better the transition from the greenhouse to the icehouse. But that record was not recovered, because what we found was a 12 million year hiatus. And the hiatus brought us back to the early and middle Miocene warmth and cooling. And then right above, we had the early Oligocene first glaciation, so the OI1 event sediments. I want you to notice the recovery column here. It's right here. This is on the left here. The white spots are the sediments that are drilled but are not recovered. And this is the challenge that we face when we drill in Antarctica. And this has been a highly criticized in science panels. You know, why do you go to Antarctica? You don't get a complete record. But please notice this, because then you will see how much we extract for what we recover. And not only that, we were able to have, this is an age depth model. Here is the age, and here is the depth of the site, and with diatoms, and then with nanofossils, and then with dinocysts, we were able to date this record beautifully. And here is this big hiatus I was telling you about that marks the transition from the greenhouse world in this site to the icehouse world at this location. So what did we find in the earliest Eocene? Well, around 52 million years ago, this is around the Eocene, early Eocene climatic optimum. Pollen contained in the sediments from the Wilkesland margin contain pollen that very much resemble the pollen of the living palms today. And if we look at what the temperature they can withstand, the mean annual temperature for palms is more than 13 degrees. But most importantly, is that the cold month mean for these palm trees is above 5 degrees plus or minus 3. The minus is lost there. So they can be in cool places. But with this palm pollen, we also had pollen that most resembled to the extent, so those living bombacaceae of today, which they are the baobabs. And the baobabs are much warmer. They have mean annual temperatures where they live of around 17 degrees centigrade. Again, the cold month mean temperature is more than 10 degrees plus or minus 3, and that puts us in a very warm Antarctica at that time. It's not only the pollen that is giving this evidence, but also some of the organic materials that were in these sediments, both terrestrial indicators and marine indicators for paleothermometry, shows that the mean winter temperatures at this time in the early Eocene in Antarctica, in the Wilkes Land margin, were around 11 degrees centigrade, and the midsummer temperature was 21 degrees centigrade, quite warm. In fact, when you look at these temperatures, what it means is that in the early Eocene, the latitudinal gradients between tropical areas and the poles was not as much as we have today. Yes. We do see, after that, a cooling into the middle Eocene. And if you recall the isotopic curve, we do have a turn after the Eocene climatic maximum into the cooling. And it's in this cooling that we have species that are similar to what it was observed in the Seymour Island record. This is just to show that at the same time that the early Eocene maximum of the Wilkes Land is a time where the site that is now in deep waters was located in a shelf location, very shallow, next to a low-lying land in Antarctica that was actually bathed, with this upper graph here on the right, by a warm current, the Proto-Lewin current, because the Tasman seal had not been separated again, and therefore the cold waters of the Ross Sea Gyre were not entering in this area yet. Then we had subsidence occurring, we had the formation of the ice sheets, we have the introduction of these cold waters from the Ross Sea Gyre. It's not so much the detail about this graph, but I'll go to this one. But what I want you to remember is that when we talk about the early Eocene, we're talking about a very different world from today. The continents were not located where they are now. This is a reconstruction for 34 million years ago. This is already when the Tasman seal had separated from Antarctica. But the Drake, still we don't know, because again, there's many question marks about this. But in the early Eocene, the seal that is represented in this upper graph had not been broken yet, and the Wilkes Land was bathed by this warm current. So the question would be, are these warm temperatures that we are observing in the Wilkes Land margin, these baobab-like tree paratropical environments, are these just local? Are these just from this margin in which we have this current here that is bathing our coastal areas? Is this representative of other areas around Antarctica? Was all Antarctica quite warm? We don't know. We don't know. We need more records about that. Also to consider is that Antarctica was very different to what it is today. And when we conduct paleotopographic reconstructions of how Antarctica was at 34 million years ago, just as a reference, I'm going to put here the last bed map. This is present. If we were to remove all the ice and we were to readjust for isostatic adjustment, what we would see is that Antarctica today, all this West Antarctic that is covered by us, would be more of an archipelago. There is lots of water here, so that means that the ice sheet base is land on water, is grounded on sea level. And the same is true for these parts of East Antarctica where we have these big tongues entering into the continent, these subglacial basins. This one is the Wilkes subglacial basin, and this is the Aurora subglacial basin. But in the past, 34 million years ago, this was not the case. And when these reconstructions take place, taking into consideration not only isostasy, but the removal of the material that has been removed from the continent, we end up with this subglacial basins where there is now water, there were low-lying lands. And our sites in the Wilkes Land are around these coastal areas, and the Seymour Islands are around here. And again, the West Antarctic also was covered by more land area, which could support more ice. So when we look at paleoenvironmental reconstructions of the early Eocene and the Middle Eocene, we should keep into consideration that, yes, they provide us with key boundary conditions for models of how the Antarctica look under a high CO2 world and high temperature world. But the climate system was not the same as it is today. And therefore, you cannot have this as an analog, and it's wrong to talk about those as an analog. But what we could use as an analog, or closer to an analog, are the Pliocene worm records. And this is the isotopic stack by Liesiski and Ramo from 2005. Here is present here, and we go back to 5 million years to the right. Here in yellow, there is the line of the CO2 concentrations that we have today. And as you can see, these concentrations have not been experienced on Earth since around 2 to 5 million years ago, and then, of course, earlier on. The global cooling with the Northern Hemisphere glaciation is shown here with this trend, starting with this cooling around 3 million years ago. And this is where we want to focus our attention. This is a time here on the left where we had the CO2, 2 to 3 degrees centigrades warmer, and the ice sheets, the continents, and the oceans locations were similar to that of today. So this is more similar to our climate system. So we could consider this as a good analog for the coming decades. So what we know about the Pliocene, this is an Andril record that Andril did collect the materials from the mid-Miocene to present, but the record of the last 5 million years, here is the lithostratigraphic column, it contained a record of glacial, interglacial variability and a record of advances and retreats of the ice sheets. And actually, they account for 38 glacial, interglacial cycles in the last 5 million years. This was very important when it came out because until that time, there was a big controversy about the Pliocene stable ice sheets versus the Pliocene dynamic ice sheets. There was many people in the community that thought during the Pliocene, the ice sheets were extremely stable and there was no way you could remove them very easily. This came to demonstrate that maybe not, and maybe the system was more dynamic than we thought. Here's just to show you a close-up, let's say, on the materials they recovered. The green materials are diamictons, and they were laid beneath the ice. They were subglacial tills. The gray materials, they were laminated, more laminated, with lots of gravel. And these are closer to the conditions that are today with the ice shelf and the floating ice. And then there were these yellow sediments that were diatom oozes or diatom rich, and these are the sediments that indicated that that site was under open water conditions and the ice sheet had retreated landward. The modeling that was conducted by the Comtois and Pollard showed that at times where these diatomites or these diatom oozes did deposit, there were times that the West Antarctic ice sheet did collapse completely at times. So the summary of the record of Andril is that from 5 to 3 million years ago, they have long periods of open oceans, like the picture above. From 3 to 1 million years ago, they're experiencing a cooling. From 1 to present, there's the current glacial conditions. That's a very frozen base. The ice is very frozen to the base and is not as dynamic as it was in the past. And the key is that, yes, we could get collapse of this West Antarctic ice sheet. But again, when you think about this, it's only one point. Antarctica is quite big. West Antarctica is quite large, and we have one point that is indicating the collapse of the West Antarctic ice sheet. When we look at the far field records, here is a compilation by Miller et al. In 2012. We do see that the sea level during the warm Pliocene was between 20 and 22 meters higher than today. And then if we think that, well, the proximal geological records from Andril, what I just showed you, does indicate that the West Antarctic ice sheet could contribute. The ice sheet model by the Konto and Polar shows that 7 meters could be contributed by the West Antarctic ice sheet during the Pliocene. And the Greenland ice sheet also contributes 7 meters according to the models by Dolan et al. If this is the case, and then yes, we do have collapse of the West Antarctic ice sheet, we believe that just one point that we have here, we should then get sea level contributed from other places from East Antarctica, which is Antarctica has been until now thought to be the most stable thing in the whole wide world. You don't melt that ice very easily. So 2 points. Maybe we need another record of the West Antarctic ice sheet from other areas around here to confirm this collapse of the West Antarctic ice sheet, to constrain better these models. And we should be looking into the East Antarctic ice sheet to see where it could be contributing to sea level. And that's one of the reasons why we looked at records of Pritz Bay, which are here at the base. But again, Pritz Bay is not a site that is located in a coastal position, is located in a distal, deep sea position. So what we get from Pritz Bay is these wiggly lines, which are giving us an idea about the glacial, interglacial cycles as pictured in the ocean, but is not giving us a picture of the advances and the retreat of the grounding line like we did get in the Andril record. What they give us, however, is an indication that sea surface temperatures were much warmer than today, about 5 degrees warmer than today, around 3.6, 3.8 million years ago, and then there was a cooling to 2.7 to 4 degrees into the 3 million years. So we went to drill the Wilkes Land margin because the Wilkes sediments, we hoped they were going to capture the instability of the East Antarctic ice sheet because they are in front of the Wilkes subglacial basin. Again, this is the place where the ice sheet is grounded below sea level, so it's potentially more unstable. This is the record that we obtained from one of the deep sea sites, and we don't go into the detail, but we have physical properties. We have, I cannot see from here, but I think this is the barium and aluminum record, which tells us about productivity. This is opal and diatom records, and these all are, again, are wiggling back and forth with the red showing us the interglacials and the white in between representing the glacial cycles. So again, we do see lots of variability, but we cannot say much about the grounding line. However, in this site, what we found is that the neodymium isotopes did show that during the warm intervals, those marked in red here, the provenance of the grains in the sediment was different than when we had interglacials. And not only that, is that the grains were, had a signal of an outcrop that is located within the Wilkes Land subglacial basin. So the ice sheet seemed to have retreated back into this Wilkes Land subglacial basin in order to erode those sediments and bring them to the site. While during glacials, the ice sheet is located closer to the present positions or even further away, and then the provenance comes from other places. We also have records from the continental shelf. Again, those are the records that we only take bits and pieces when the icebergs are letting us. And we do have indications that in some of the warm intervals that are seen in the deep sea record, like this one here or this one here, around 5 million years ago, we also see that the grounding line was positioned landward from the site. So there is indication that the ice sheet retreated. And new modeling by the Konto and Polar are now considering ocean warming accessing the base of the ice sheet and also taking into consideration the steepness of the ice at the border. They are getting some retreat into these basins. So it could be that it's coming from this side. But if we are melting here in the Wilkesland subglacial basin, you would think you would also will be melting here in the Aurora basin, where there was this entrant of water that I was showing you before. But we don't know because we don't have records here. So in general, for the Pliocene, this is Pritz Bay on the left. This is a distal record. That means glacial, interglacial variability, but no idea of what the grounding line is doing. These two are Wilkesland records in the middle. Again, distal records, interglacial, glacial variability, grounding line. We do have a little bit more constraints there because of the provenance studies and the modeling. And here we have the Andril records, which in yellow are the times where the West Antarctic ice sheet is thought to have collapsed. So we are getting a picture of how things are looking around Antarctica. We're getting better at, but we still are faced with this problem that when we have in one region a distal record, we cannot link it to what the ice sheet is doing. If we cannot link it to the grounding line advance and retreat, we cannot talk about ice volume changes, and therefore we cannot really talk about comparisons with the far field sea level record. So that's something we need to work on. So we are talking about how at 1.34 million years ago, we went from the greenhouse to the ice house. We have been in the ice house for 34 million years ago, and now we're going towards warming, maybe into the greenhouse, we don't know. But what is important to understand is what are the mechanisms that are forcing these changes. And it used to be that we only thought about these continents moving away and creating a thermal isolation of the Antarctic continent, isolating it from the warm currents from the equator reaching the coastal areas of Antarctica. But this may not be enough. And actually, when you have modeling of how the continental ice sheets grew in Antarctica, the opening of the seaways are not enough to allow for the continental ice sheet to grow. But the decreasing in CO2 concentrations do have the power of having the ice sheets kicked in. We, of course, have always orbital forcing. We know that our Pliocene records are paced by the obliquity, and the early Eocene are paced by the eccentricity. And now we have another mechanism that recently has been observed, and is these warm waters upwelling to the shelves of Antarctica and warming these ice sheets from the base. We need to understand better about the mechanisms, and for that we need sediment records that will provide us a better calibration for the models to constrain these forcings. So in summary, what I hope I was able to convey to you is that what we are seeking is to conduct paleoenvironmental reconstructions in time and space of these ice sheets and what these ice sheets were doing and how they were behaving. The sedimentary records, together with the modeling, they also provide us with mechanisms for change. And with this, we build our reference scenarios. But we do not have enough data. You have seen there is data of Antarctica. They're not samples at all. Where we have samples, we are missing these distal proximal correlations, and therefore we are unable to provide the needed boundary conditions to this model to build these reference scenarios. So we do have to if we are to understand how the ice sheets respond to elevated CO2s and temperatures that we're facing in the future, sometimes to use as analogs, sometimes to inform of the potential changes, the mechanisms involved in these changes, like in the early Eocene, we are going to have to get more records. And the ocean drilling programs do play a major role into getting these records. They are right now the ones that have the technology to access this record. The European Consortium for Ocean Drilling operates mission-specific platforms. These are the ad hoc ships. They can get ships that are icebreakers or that can drill in shallow areas. And these are the kind of platforms that are very much needed in the polar areas, together with the JOIDES resolution, which is operated by the IODP US, that is giving us more the distal records. So a very, very valuable program. In the meantime, the community has gotten together because, as I have shown you at the beginning, these areas are difficult to access. It's very expensive to access these areas. So we cannot just have a bright idea of just let's go here, let's go there, and let's see what happens. But we need to have a community coordinated strategy of what are our priorities, and we need to prioritize within these priorities. So this program that is called PACE, Past Antarctic Ice Sheet Dynamics, is a research program of SCAR. And SCAR is the Scientific Committee for Antarctic Research. And what we're trying to do is to obtain the records of past warms from areas of the Antarctic that we know they're vulnerable. These are the areas where we see rapid melting, rapid ice stream speeding up, and of course, these subglacial basins that I was showing you from East Antarctica. This strategy, of course, is to get records from continents, so these outcrop records that are so few but are so important. When we get technologies to access the subglacial record, with the UNDRIL and the mission-specific platforms, we really need coastal records of grounding line advances and retreats. They're key for understanding ice volume changes, and with JOIDES resolution-like technologies to drill into the deep sea areas. In this strategy, we need to consider the ice sheet model that needs to, in turn, to consider paleotopographic constructions. Otherwise, the ice sheet models may not be good enough for the different time slices. So this is a map of where we're going as a community in Antarctica. And in yellow, you see the previous sites that have been already drilled. We do see in maroon the ones that were drilled by the, that are planned for the UNDRIL program. And then we do have also in blue the subglacial lake drilling that has been planned or accomplished. And in these numbers correspond to proposals that are right now in the IODP system in different stages. Like, for example, this one in the coastal areas of the Wilkesland margin is now penciled in for scheduling, as well as one in the Amundsen Sea. So that's the picture. The gray extended shadows means that we need these latitudinal records because we do not understand at all this day what are the ice sheet ocean interactions. What is the ocean doing when an ice sheet is growing? What is doing when the ice sheet is retreating? And just one more point is these programs require lots of people, required of lots of international collaboration. This is just an example from the IODP expedition to the Wilkesland with 29 scientists on board of 19 or 20 nationalities, if I remember well. Then about 40 to 50 more working in the sedimentary records that are working in their labs. And you need to get involved. There's lots of young people in this room. This is a program that it's an open opportunity, both the IODP or the PACE program of SCAR. And with this, I leave it here, and I thank you with your attention. Thank you. Good.
Okay, thank you very much, Carlota. I'm afraid we have time for maybe a couple of questions because we have to move to the sessions. If there are any questions that you would like to put to Carlota right now? Okay, otherwise, she will be around today, and I'm sure she will be happy answering to your questions. You can stop by the IODP booth too. And before you move out, I would like to let you know that all these plenary lectures, as well as the opening ceremony, are available at the media server from the university. I will put the address in all the screens, and you can see all this presentation. The opening ceremony is already online from this morning, okay? And just last but not least, as we mentioned in an email that we sent last week, at the end of last week, there have been some changes in the original program that you have printed, because these changes were related to very late cancellations. So please, the one that is really the program that we actually will follow is the one that is online. So check the online PDF in the meeting website. And if you have any questions, please ask us, any of the staff members. And with this, I thanks again, Carlota. And enjoy the afternoon talk.